In this unit, we're going to discuss the structure and reactivity of compounds of hydrogen. Hydrogen is the simplest element, but it's actually highly appealing in some ways because it is so small and so simple. For example, hydrogen has been thought of as a potential fuel because its combustion, its reaction with oxygen, is a very simple reaction, gives only water as a byproduct, and is highly exothermic. There's a whole research area centered on a hydrogen economy with hydrogen as kind of the foundational fuel there. It's not without its issues because hydrogen in elemental form is a gas, but a lot of research is being done to find ways, for example, to store hydrogen in solid form in compounds with other elements in such a way that it can be reversibly added or removed from the solid toward the aim of the hydrogen economy. So this is one motive for studying hydrogen-containing compounds. They're also just a great kind of playing around ground for Lewis acid-based principles, since, as we'll see in the ensuing slides, hydrogen has kind of a dual nature in compounds. It can be either electrophilic, and we've actually seen that a lot, or nucleophilic, depending on what it's bonded to, what it's paired with in a compound. Now, the hydrogen atom is, of course, the simplest of all atoms, a single proton in the nucleus and a single 1s electron when in neutral form. So this is an atomic symbol for hydrogen and a simple atomic orbital energy diagram with just one up-spinning electron in the 1s orbital. The configuration of neutral hydrogen is 1s1, and a simple picture might have the one proton at the nucleus surrounded by the spherical 1s orbital containing one electron. Right? Hydrogen does have two other important isotopes that I felt compelled to mention here. The hydrogen-2 isotope is better known as deuterium, and hydrogen-3 is better known as tritium, and these just have neutrons in the nucleus, either one neutron in the case of deuterium or two in the case of tritium. Now, from a chemical point of view, hydrogen has properties similar to both the alkali metals in group 1 and the halogens in group 17. And on some periodic tables, you'll actually see hydrogen written in both places to reflect this sort of dual nature of the element. If we think about the hydrogen atom can lose an electron to form a proton, H+, right? H+ is just a proton, since if we remove the one electron from H, we're left with H+ and only a proton in the nucleus. This is reminiscent of the oxidation reactions of the alkali metals. For example, when sodium metal undergoes oxidation, it forms Na+ and loses one electron. Hydrogen can do a similar thing to form the proton, H+. But hydrogen can also gain an electron to form the hydride anion, H-. And this is particularly appealing as it leaves hydrogen with a full N=1 shell. Right? And so this is something that hydrogen can undergo in the presence of a suitable reducing agent, for example, to form H-, and this is reminiscent of the reduction reactions of halogen atoms, or even the elemental halogens like Cl2 and Br2, where they pick up electrons and form halide anions, Cl- and Br-. The hydride anion is analogous to the halide anions in this respect, although, as we'll see, it is much more basic than the anions of those much more electronegative elements. Binary hydrides are going to be our main focus. These are compounds that contain hydrogen with only one other element, and the nature of that other element dictates the nature of the hydrogen-containing compound, and electronegativity here and the type of element is really key. The three categories are ionic, metallic, and covalent hydrides, and I wanted to start with the ionic and metallic hydrides because covalent hydrides we've already seen and worked with extensively, as you'll see on the next slide. The ionic hydrides contain hydrogen together with a main group metal M. This is typically a metal in group 1 or 2, an alkali metal or alkaline earth metal. And the situation here is that H is much more electronegative than the element M. And so in the compound, what we have is really an ionic compound with a metal cation paired with the hydride anion, H-. And that hydride anion is nucleophilic and Bronsted basic, Lewis basic and Bronsted basic hydrogen. And examples of this would be compounds like lithium hydride, LiH, sodium hydride, NaH, magnesium hydride, MgH2, things like this. That nucleophilic hydrogen is going to want to donate its pair of electrons to Bronsted acid or Lewis acid, for example, in the ionic hydrides. And they're generally solids, right? They're solids just like any other ionic compound of lithium, sodium, or magnesium is going to be a solid. The metallic hydrides, the name is actually reminiscent of these ionic hydrides with a metal and hydrogen, but the metallic hydrides specifically contain a transition metal together with hydrogen, and transition metals are not quite as electropositive as the group 1 and 2 metals, and so the situation we end up in here is more of a mildly nucleophilic hydrogen situation, with the hydrogen metal bond being something like a polar covalent bond, but not polarized toward the metal, polarized toward the more electronegative hydrogen atom. So the hydrogen is still nucleophilic, but not so much as in an ionic hydride with a group 1 or 2 metal. An example of a metallic hydride compound is this compound. It's known as Schwarz's reagent, or zirconocene hydrochloride. You don't really need to know the details of this coordination complex, just that this is zirconium-4 with a couple of carbon-based ligands, X-type ligands, and a chloride ligand. Not so important. Our big point of focus here is on the zirconium-hydrogen bond, and hydrogen is more electronegative than zirconium. This makes the hydrogen in this compound relatively nucleophilic, and in fact, this compound can be used as a reducing agent, as a source of hydride anion 4 reduction reactions, and it commonly is. But it's not a full-blown ionic bond. It's not Zr plus and H minus. This is more along the lines of a polar covalent bond polarized toward the hydrogen atom. Now, the covalent hydrides, whether you may know it or not, are actually highly familiar to us. These are compounds containing hydrogen and a non-metal element X, and in fact, we called these binary acids back in the unit on acids and bases. Because the non-metal X is more electronegative than hydrogen, generally we've got a covalent bond polarized toward X now, with the hydrogen containing partial positive charge. And so these tend to be Bronsted acids, especially when X is a relatively electronegative element. Examples are things like CH4, NH3, HCl, HBr, HI, all of those binary acids that we're familiar with from earlier studies. And the reason these tend to be Bronsted acids is because X, being a nonmetal, is relatively electronegative and is generally more electronegative than hydrogen. At this point, we've seen the 3 classes of hydrogen-containing compounds, and in the next video, we're going to begin exploring the reactivity of these compounds. To some extent, we've already touched on this, seeing how ideas about reactivity flow from the structure, right? This hydrogen looks electrophilic, while this hydrogen looks nucleophilic, for example. We're going to bring those ideas into more focus in the next video.